This video is presented to you by Physics for Students.
Tensor products. In this video we would be looking forward on what is called a tensor product. Initially I was willing to make a video, a single video which will contain all the tensor operations. However, I found that tensor product itself is such a vast subject that I need to make an exclusive single video on tensor products. The topics that we would be covering in this video are definition, what is called an outer product, Kronecker product, what is the tensor product and how we can build on tensor products. We are also going to look forward for what is the application of tensor product in quantum mechanics, what are the rules of Kronecker product, non-decomposable tensor products, and how can we write and understand multiple tensor products. So this is the agenda of our video today. First, we need to look forward for what is the definition of a tensor product. The tensor product of two vector spaces V and W, denoted by V multiplied by W, is also called the tensor direct product. It is a way of creating new vector space. Just note that we would try to maintain this convention of taking two vector spaces as V and W, and as you see on the right hand side of your screen, V multiplied by W is noted by red because this is the notation in which we are going to look upon. So this multiplication sign which carries a circle around is basically called the tensor product. So you can understand this is a new way of constructing new vector spaces. Now if I take Rn and multiplied by, you can call it as a product of R super K. So these two indices Rn and K is more or less equivalent to Rnk. So this is two set of real numbers which gives to a new set of real numbers with their indices right on the top. So tensor product also obeys the distributive law, the law of distribution, and as you can see I have denoted the following. This is the something which is similar to A. If you take U, V and W as A, B and C, then it would be A multiplied by B plus C equals to A multiplied by B plus A multiplied by C. This plus sign is the same. We will look into another video what it is called. It is basically a notation of tensor addition. So this one is the tensor addition and the other one is the tensor product. Now algebraically, if we look into the vector space V and W, which is spanned by the elements of small v multiplied by some small w, then we can take alpha as a scalar, and what we do is that we get this. So these are the following things which are satisfied. This is the first one, the second part, and this is the third part, and a consequence of all these laws or whatever the rules they are mentioning, that following is also true, the last one which is the 0. So what we have done is that we have taken your vector space V and W spanned by the elements small v small w, taking scalar as alpha, we get this one. All these laws follow. The second definition of tensor product which we are going to explain is something which is related to group theory, because group theory closely deals and intricate details of tensor products also features in group theory. So tensor product also comes into play when we are dealing with group theory. So this is a nice definition which you can read through your screen, which I'm not going to read it again. It is quite self-evident, and tensor product of two unitary modules V1 and V2 are an associative commutative ring A, and is the module V1 multiplied by A V2 together with a bilinear mapping. So the tensor product of the two unitary modules are given by this, right? And this one, the above this equation is always universal in the following sense, right? So this follows the blue arrow down. It means that it is universal for the following: any A bilinear mapping, this expression where W is an arbitrary module, there is a unique A linear mapping, right? So this is how it follows, and also for this, right? So For any bilinear mapping, this one where there is a module, there will be a unique A linear mapping which is given by this, and this one beta x1 x2 equals to b x1, the tensor product x2, and x1 is an element of v1 and x2 is an element of v2, which are two associative commutative ring which we have denoted earlier as two vectors. Now when we are going back to what is called a tensor notation, right? So in general, a tensor notation is denoted by this, A multiplied by D, or it can be V multiplied by W, anything. So this cross multiplication along with the reds with the circle around, it actually denotes a tensor product. Some books uses this one, A super I, B super J equals to C superscript of I and J. So if you find the right part of the notation, don't get confused. This is also a tensor product. Some books omit that. So we will look into higher order of tensor and how the product looks like, the indices, how they change. But first we have to understand the following things. What is a direct product? What is an outer product? And what is a Kronecker product? Once we understand these three concepts, which we will touch base briefly in this video, we can quickly understand how a tensor product is formed. So in order to understand what is a direct product, we will go back to group theory again, and let us take two groups G and H, which is a direct product G multiplied by H, right? The cross denotes the direct product. Given group G and H, so the direct product is defined as this. So you can call it something like G is an element of capital G, H is an element of capital H. Now let us consider capital G and H to be groups. The direct product of G multiplied by H of G and H is the set of all ordered pairs as this, right? It is a set of all ordered pairs which is followed by this and which is followed by this operation. So yeah, so this comes true. So I think you can quickly take a note if you want that what is a direct product in terms of group theory and how the sets and their elements are related to each other. Okay, so if we get R as a set of real numbers by the group of real numbers, then this one R multiplied by R is the group of all two components, which is this, right? R and R is the group of all vectors given by this x1, y1, x2 and y2, and this G1 multiplied by G2, which are the two groups. Here what happens is that the first component is from G1, capital G1 obviously, and the second component is from capital G2. So but this multiplication sign, just to make you a note, is the same as in the Cartesian system that we learnt in our school days, but let us not confuse between that multiplication sign which is same as here in the group when we are dealing with direct product. But I would advise, let us not get confused between these two. That was something else, this is something else, although the sign seems to be similar in both the cases for group theory and for Cartesian system. So if you get R, if you think R is a set of real number, then R product of R is this. This comes true. If R is a group of real number, then R leads to this. This one is true. If R is the ring of real number, then R direct product of R leads to this, and this one is also true. So here it is, the direct product takes the Cartesian product of sets, if you consider A and B to be two sets in the Cartesian system, then the ordered pair of elements A comma B, and applies all operation components. For example, A comma B plus C comma D is more or less equivalent to A plus C comma B plus D. So that is basically how the definition goes about. So let us see what is an outer product. The tensor product of two coordinate vectors is termed as outer product. If the two vectors have n and m dimensions, then their outer product is an n and m matrix. If we assume that two vectors, one spans from u1 to u2 up to um, v spans from v1 to vn, then the outer product is given by this sign, u multiplied by v with a circle around it, and this gives rise to this. So considering that A to be a matrix, u multiplied by v gives to this, and this is a matrix notation, and if we consider the indices, then it would be this. So it would be u v sub ij equals to u sub I v sub j in terms of index notation. So this is an example of outer product of two vectors if we follow the matrix sign and how it would be in index notation. So the outer product of u multiplied by v is equivalent to matrix multiplication, considering m equals to 4 and n equals to 3. So this one stands to be true. So u outer product of v is u v transpose, which is this one. And if u and v be the vectors, then the outer product of u and v is w u v transposed. That means this is important. W equals to u outer product v is the same as the matrix multiplication of u v transpose. This is something really important in order to know the outer product of two vectors, if you consider two vector spaces u and v, is equivalent to the matrix multiplication which is given by here. You multiplied u, v1, v2, v3, it gives to this matrix, and u and b the vectors, and the outer product is a kind of a transpose. Okay, so what we know that what is a Kronecker product? So Kronecker product is an operation of two matrices of arbitrary size resulting in a block matrix. We all know what is a block matrix, so let us not dedicate more time to understand what is a block matrix. It is a generalization of the outer product. This is very important. Obviously on certain instances or certain conditions. So it is a generalization of the outer product from vector to matrices. Both the outer product and Kronecker product is denoted by this sign. This is quite self-evident. I think I don't need to repeat it. So say for example RS, it is a matrix of A. Ith element varies Aij from I from 1 to R, and J varies from 1 to S, and B is a TV matrix. Then the Kronecker product of A and B denoted is by A multiplied by B, and the RT-SV matrix formed by multiplying each of Aij element by the entire matrix B stands to be this. Right. So don't worry, I am on the process of making a separate video on what is a Kronecker product, a little bit on the history of Kronecker and what are the essential features and what it is all about Kronecker product. So just understand for this video this part, because the details of the Kronecker product, I'm trying to make it and release it as soon as possible on the Kronecker product exclusively. So let us take this one as RS matrix, and the M and RT multiplied by SV, A multiplied by B stands this. So let's see some example. Very simple. I have taken A11, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, B equals to this, then A multiplied by B gives to this. So given an MN matrix and A and a PQ matrix B, then their Kronecker product C equals to A multiplied by B. If A is a MN matrix and B is a PQ matrix, then the Kronecker product of A multiplied B is the PMQN block matrix, which is on the right hand side of your screen. This is just a very simple example to show how Kronecker product gets multiplied and how in matrix it looks like. So this is the Kronecker product, C equals to A multiplied by B. Okay, so now we come to the central part of the video, which is how we will build and understand on tensor product. Okay, so for example, if we are given two vectors v and w, okay, which we consider to be finite dimensional vector space. So the question is that can we build on with new vectors, which are the tensor products? As we have you have noticed earlier, the definition itself says that tensor product are new vector spaces which are built upon. So can we, given two vector spaces v and w, how can we build on that? So one part is that let us consider v as in Rn and w as in Rm. So we consider set of real numbers V we take is simple as 1, 2, 3. W we take it as 4, 5. I have denoted the arrow just to make you understand that these are vectors. So this is R3, this is R2 in 2 dimension. So one part is that we take 1, 2, 3, 4, 5 and we just stack things upon, right? So we are just adding 1, 2, 3 and then we add 4 and 5. So this we call it as VW in R3, that is a 3-dimensional real set added with a 2-dimensional real set R3 plus R2. This one at the left hand side bottom screen, which is in green, this is a plus sign, which is a tensor addition sign. Just like tensor multiplication, this is a tensor addition sign. We can also do the second way. This is one way approach. If we take this part same, what we can do is this. We can multiply things on 1 multiplied by 4, 1 multiplied by 5, 2 multiplied by 4, 2 multiplied by 5, and so on. Just note that this dot doesn't mean the dot product. This is just to make you understand. So the first approach is this one and the second approach is this one. The first approach is a plus of R3 R2 and the second approach is a multiplication of R3 R2 both with V and W. So these are the two ways in which we can, given a finite dimensional vector space, we can create new vector space. Right, so this is one what we call is that the dimensions add, that is the tensor addition sign, and this is what we call the dimensions multiply, this is the multiplication sign. This is what is called VW is the direct sum, where we are just stacking things on, and this is what is called direct product, where we are multiplying things or we are doing a direct product. So let us not get confused with the terminologies. So what we get is this, say for example these are the elements, this is V plus W and this is what? This is V multiplied by W, right? And this works both ways, right? So this is just to show you a visual demonstration on the addition and the tensor product of two elements. Now this is something which you can call, which is similar to Cartesian coordinates. Given x equals to this and y equals to this, if we add this, it gives to this, right? Right. So this is something with similar set of numbers in Cartesian coordinates what we do. Now let us see a few examples. So I've just taken 1, 2, 3, 0 and we have put up a tensor product which gives to this, again this and this. So these I think are just few examples just to show you that how the elements they actually multiply and they do things upon. You can just check on the calculations whether I have made it right or wrong. So these are few examples. So what we can tell is that tensor product of a vector is a matrix, because this one leads to this, and you can see how we have multiplied and got the results, and this one also leads to this, which we can call that a 3 by 2 matrix has been rebuilt into a 6 by 1 vector, right? So this is how we do, and what is our tensor product. We are building on that. Now some text, as I have mentioned, looks like this. We can also do this one, that we can take a rank 1 tensor, we can take a rank 2 tensor, and we can get a rank 5 tensor. So here it is a rank 2 tensor, rank 1 tensor with a tensor product of rank 2 gives rise to a rank 5 tensor. But here there's a small note, covariant rank of the outer product of tensor is the sum of the covariant ranks of the input tensors, and the covariant rank of the outer product tensor is actually the sum of the contravariant ranks of the input tensor, right? So these are just examples on how tensor product actually takes place. Now just to sum up, you can understand this in a very easy language, that tensor product is actually a more generalized version of multiplication. Yeah, obviously, where you add, bunch or stack up and then you organize the result in a list more systematically. If you go back to the slides, what you can see is that we are basically multiplying and we are building on those. These are few examples, right? So this is just to sum up how rank 1, rank 2 gives to rank 5, and just a basic summary that what actually tensor product is. Now tensor product, this is just a note to those who are viewing this video, that tensor product is sometimes called a Kronecker product, which I have even used in my video. However, they are not the same. I will make a separate video on where I will be speaking about the difference of tensor product and Kronecker product. Just let us understand these are not the same. Now the next question which comes is, does every vector v multiplied by w looks like small v multiplied by w? The answer is a definitive no. Right. This is a no. Now we will look into why it is not. I mean to say that a vector in a vector space can be written as a weighted sum of basis vectors, right? A weighted sum of basis vectors which are like building blocks. So here it is, a vector space can be written as a weighted sum of basis vectors. Now if I get a kind of a this is something I think we have done similar. We will, if I get something like v1 which spans up to vn in v and w1, w2 and up to w, and I and j ranges from 1 to n, j ranges from 1 to m, then if the question is that can we combine to get a new nm vectors? So this is just similar to what we have done earlier. We will multiply the vi together with wj in all types of combinations, right? We'll take all types of combinations, and now multiplying v sub I with w sub j means taking the tensor product of v sub I and w sub j. So this is something important. So vwi is a set of all vectors of the form small v sub I, a tensor product of wj. So yeah, so this is a repetition from this earlier one. So we take n equals to 3 and m equals to c, and then we can find out the 6 basic vectors from 1 to m, and we get this, right? So all these arrows, if I have missed, my kind apologies, just to make sure that this is a vector. So this is a 6-dimensional space with bases as this. So v multiplied w is 6 dimension with the basis as mentioned right at the bottom of the screen. Now suppose that we get this v1, v2, v3 and w1, w2 as this, then what we get is this one, right? So this is just to show you how the product happens. So yeah, so you can take a note, you can take a pause, you can take a screenshot. So this is how it happens. So a column and a row vector can be operated by like this. This is just few examples to make you aware about how tensor product happens. So column and a row v multiplied by w with a1, a2, a3 going up from b1 to b3 goes like this. So now the question is that what is v multiplied by w, right, with the tensor product? However, the definition using, so let's see this. It is the vector space whose vector are linear combinations of the element v sub I multiplied by w sub j. So technically vw is called the outer product of v and w, and this is written as v outer product of w. Yeah, so that it is how it is a transpose of vw. It is as defined. This colon equals to is termed as defined. Now the term linear combination actually is wrong. This is wrong. So this definition actually doesn't work out. The term linear combination actually has no meaning unless we are speaking about the elements of a vector space, right? So the symbols v sub I and w sub j are nothing but symbols. I hope that is clear. However, if we say formal linear combinations, then it would mean that they are elements of vector space written down as symbols that represents linear combinations of them. We can say a formal linear combination of the symbols v sub I and w sub j is a function like this, right? So given a function like this, we can represent the function f as this, right? The set of such functions form a vector space where addition and scalar multiplication are defined. This is important. I repeat, the set of such functions form a vector space where addition and scalar multiplications are defined. This addition and multiplication corresponds how we write this one, which I have shown it earlier, this one, and if they actually are linear combinations, so we can say this: tensor products of vector spaces, right? So sorry. Yeah. So this is important, that the term linear combination has no meaning unless we are speaking about the elements of a vector space. The symbols vi and v sub I and w sub j are nothing but symbols. However, if we say formal linear combinations, then it would mean that they are actually the elements of vector space written as symbols as noted. And I would like to show you again formal linear combination of the symbol v sub I and w sub j is a function which is denoted by this, and only when we are given a function then we can represent function f as this, right? So the set of such functions of vector space where every things are being defined, this addition and multiplication corresponds to this equation. Actually, then we can say if they are actually were linear combinations. Okay. So this is a kind of a small animation that I have shown just to make you understand that these elements right from the right hand side, which are coming down and creating a vector space. So we can tell that big vector space is created out of two or more small vector spaces, right? Yeah. So these are actually forming the vector space. So we can call it like this, and even we can extrapolate it further. So let us look a little bit more into the tensor product. Let us suppose that V and W are two vector spaces, and we have got E1 to En and F1 and Fn be the bases of V and W. Then what we get, we define nm basis vectors on this, right? I equals to n and j equals to m. So tensor product is a bilinear, right? This bilinear means this, okay, is linear in V and W, V, and also is linear in W, right? Linear in V and linear in W. If they are more than two vector spaces, then we can call it multilinear vector spaces. It means this and this, right? So in other words, the coefficients are given by V sub I and W sub j, right? And tensor product of W is spanned by the vector basic vectors E sub I and F sub j. So in order to explain things better, what I explained to you earlier, we can explicitly write this. If we take n equals to 2, m equals to 3, then nm 6, then these are the new basis vectors which gives rise to this, and this. This is something which we have explicitly written for you so that you understand. And the tensor product of the general two vectors V and W is given what you see on the right hand side. Now we come to the application of tensor product. Although there are multiple applications of tensor product, however, we use quite well in quantum mechanics. Now, if we get free particles in 3 dimensions, and they has, let us assume that they have 3 dynamical degrees of freedom, right, which is this: p sub x, p sub y, p sub z. These are 3 dynamical degrees of freedom. Now, note that we can specify p sub x or x, hence such dimensions give only 1 degree of freedom, right, which we all know is not in classical mechanics. So the momentum eigenket is this, right, which forms the basis of the Hilbert space h sub x. The eigenstate of the full Hamiltonian, if I write it down, is the tensor product of the momentum of eigenstates in x, y and z direction. So if I take the x, y and z direction, so the eigenstate of the full Hamiltonian is this. Just note that I have used the bra and the ket notation. So the bra and the ket I have denoted by this sign, which I have actually drawn it because otherwise it doesn't look good. The operator which we used, p sub x, is this, and this is actually the Hamiltonian. I'm so sorry, it's quite long, so it is a little bit smaller, which I have written, and the complete Hamiltonian is this. So this is the complete Hamiltonian, which is written in blue in the box, and the operator is this one, right? So just before we wrap up, quick rules on the Kronecker product or the decomposable tensors. So if we get a kind of a matrix like this, we take a block matrix like this, then one, the distributive property follows, which I don't need to explain, it's quite okay with you. If we take alpha as the scalar which we have taken earlier, then multiplication of scalar rule follows, the associativity rule follows, the zero matrices rule follows, also the inverse rule follows. Inverse rule, I think it's quite easy to understand. Then the mixed products are also there. The mixed products rules is follow, the rules for computing, and finally the trace rules follows, and the transposition rules where you transpose the elements like this. So these are the rules which follows from the block matrix which is taken. So you can just take a note how these rules are there. Now, non-decomposable tensors are the result of weighted sums of the decomposable tensors. So we'll just explain you in brief, like what is this. Let us consider, for example, an arbitrary matrix x equals to x sub tj in the order of t multiplied by m, right? Yeah, it is there. This can be expressed as the following weighted sum of the contravariant tensor products formed from the basis vectors, this one and this one. So we compute this. So the indecomposability lies in the fact that the elements of x sub tj cannot be written as the products of an element. This is important. And indexed by an t and an element indexed by j. Yeah. So this is actually, from this, the following we can deduce actually the tensor products like this. Yeah. Just let me quickly explain you the notations. Here x prime is the transpose matrix, xc is the long column vector, and xr is the long row vectors. So just note that in the forming of xc and xr from x, the index that moves assumes a position at the top of the head of the string of indices to which it is joined. So the subscript c and r denote what is called vectorization operators. So we come to the last part, which is the multiple tensor products. So for example, if you assume this one be arbitrary matrices of order say Tm and Sm, then we get this. Then the tensor product, also known as the Kronecker product, is this. And E sub Lk Ji Stmn for the matrix order of Stmn with the unit in the row, this one, indexed by Lk, which is this row, Lk, and in the column indexed by Ji. So this is the part in which we are forming the indices. So indices Lk are not ordered, remember. That means this one. So if I take this, it would mean this. So this is a kind of a much more explicitly written way of notation. Okay, so I think that brings to the end of the video. We learned it has been a little bit longer video for me to even make people understand. So we spoke about the tensor product, which actually included a lot of topics, subtopics, Kronecker, outer product, and decomposable matrices, decomposable products, tensors of higher dimensions. So all taken together, I think I have been able to give you a clear picture of what and how a tensor product operates and how tensor products are. If you have any further comments, please put it up, and I'm coming up with a new video which we am doing. It is on Kronecker product. This is important. Kronecker product, the features and the properties of Kronecker product, which would be the topic of my next video. Let us stay safe and stay happy, because the coronavirus is again on the rise. But Physics for Students will try to bring up more interesting things so that you don't think of the current pandemic, and you enrich your brain, make it more fertile with physics and mathematics. That is all from my side. I think you like this video. I would wait for your comments and any kind of a mail or whatever you like to do. I am thankful to the new list of lot of new subscribers who are subscribing to my channel, and I'm doing my best to bring new things upon. Stay safe and stay happy. This is Kronecker signing off from Physics for Students. Bye.